the actual lecture part. So using scientific notation, evaluate this calculation. So now it's already shown in scientific notation for us, right? And so I just put now, because it says to do it in scientific notation, I assume they want me to do something a little special with it. So what I'm going to do here is I'm going to rewrite this 1.4 cubed times 10 to the 9th cubed and 9.3 squared times 10 to the 8th squared. Is this absolutely necessary? No, but it's showing that I understand how they work. What's 10 to the 9th cubed? Okay, you just multiply that 9 by the 3. So it's 10 to the 27. So this here is, whoops, this here becomes, come on, why did that? Okay, let's just say I don't know what I'm doing as much as I think I am, or as much as I think I do. I was pretty sure that I simply changed my pen to blue, and it shouldn't have done that. So this here is not drawing, it's moving. Anyone else feel frustrated? No, because you're not the teacher who's doing it wrong. Okay, because this is, look, it did it again. Now it's writing. So this here goes to 10 to the 27 and 10 to the 8th squared, using the same rule that Max did. Somebody else, what's 10 to the 8th squared?
10 to the 8th squared?
10 to the 16, because you just multiply the exponents. So this here is 10 to the 16. That's 16. Now, what's 10 to the 27 divided by 10 to the 16? Do you know what the rule is for that? It's very simple. You subtract the exponent from the lower one from the exponent from the upper one, as long as they're both the same number. So it's 10 raised to and 10 raised to, so I can use that rule. Just like, well, yeah. So 27 minus 16 is 11. So what I'm left with is 1.4 cubed over 9.3 squared times 10 to the 11. Now I need to get out the calculator and see what 1.4 cubed divided by 9.3 squared is. And I'll have that number times 10 to the 11. Now that number is going to be less than 1. So somebody go ahead and calculate. Let's just get the answer. Okay, so we have 0.0317. Is that what you said?
Yeah.
I have faith in you.
I'm not sure.
So I have 0.0317 times 10 to the 11. If we use scientific notation, how do we actually want to show the number? We want one digit and then the decimal point. So how many times or how many places do I need to move the decimal point? 2. And because I'm moving it to the right, it's a smaller number. The exponent's going to have to go down by that 2 that I went down. So I'm left with 3.17 times 10 to the 9th. Now, if you just write 3.17 times 10 to the ninth, which is what you get if you just put it in your calculator, you'll get 1 point, right? You need to show that you understand how the times 10 things work. Max, question.
Would you do just 3.2 because of significant digits, or is that not?
In real life, yes, I would.
Okay.
In astronomy class, I don't pay attention to it so much.
Okay.
That's in real life. In my physics classes, I would be, now, how many significant digits? We only have 2, so the real answer is 3.2. You're right. Now, number 5, I'm not going to do. You know why? Because I did it in class. I already did it in class. You can go back and watch it again on YouTube if you want. Or you can look at the notes from the last class going, on Moodle and looking at the notes and see it there. And, given that we don't have an infinite amount of time because I've already done it, it would just be repeating the explanation. But number 9. Number 9 was one I said, I think it's going to be difficult. Come talk to me. We'll work it out. So we'll work on it. So number 9, and thankfully I did have it. If 1 year equaled 365.170 days, what would a reasonable leap year system be? Has anybody actually worked out a system?
I just say we have 0.17 of a day.
Well, what we want to do though is have integer days. So X number of years, we add a day. X, Y number of years, we take away a day. Okay, Max said he had a solution. Did you have a solution, Daniel? No. Okay. So, not telling us what your solution is. Tell us how you started, Max.
I just started by using our base leap day system. So just 1 leap, 1 leap year every 4 years.
Mm-hmm.
And then from that, I just figured out which fractions to. So how I just feel like the Gregorian calendar is take away 1 every 100, add 1 every 400.
Mm-hmm.
So I just figured out fractions like that. They would get it from 0.25 to 0.17.
Okay, now that's an approach. And remember, there are a lot of ways you can come up with this. I'm going to go with a different approach, right? So this is not saying that his method is wrong. There are lots of correct methods you could come up with. They're all going to have the same essence when you get down to the end of it, but they can look a lot different. The way I'm going to start is take 1 divided by 0.170, right? The fraction was 0.170. Take 1 divided by 0.170. What is 1 divided by 0.170? Someone with a calculator? Okay, 5.88. That's close to 6. So I'm going to make my leap year system start with a leap day every 6 years because that's close. Now, why did I say I'm going to add a leap day, not take out a leap day? Why do I need to add a leap day?
Because
it's more than 3 years.
Yeah, because it's more than 365 days in a year. So I'm going to have to add a day periodically to get better. So my rule number 1 will be add a leap day every 6 years. Right, so you can see I'm starting differently than Max did. Doesn't mean Max was wrong. It's a different scheme. So I'm going to add a leap day every 6 years. If I do that, 1/6 is equal to 0.1. What is it? What is 1/6, everybody? 6. It's 6 repeating. So now I'm short by that much, 0.0033 repeating. What do I do now? Well, 0.33 repeating, if I take 1 divided by 0.033 repeating, you probably know 0.33 repeating. Oh, I left. I have the wrong number of zeros, everybody. So if it was 0.33 repeating, that would be 1/3. 0.033 repeating is 1/30th. This is 1/300th. What does that mean for my leap year system?
Add a day every 300 days, every 300 years.
And then I'm perfect. Now, if you look at that system, the system is actually really wonky because every 300 years, what am I doing? I'm adding 2 days in the same year. So I would probably do something to offset it, like, do the 300 years on the half interval between the 6 years so that I don't have 2 leap days in 1 year, because that would be pretty weird. But that's a system then that's going to work. And if you look at that, what is the entire system? In 300 years, I'm going to have, 300 divided by 6 is what, 50? So I'm going to have 51 leap days in 300 years. If you have a different system and it comes up to that same number of leap days in 300 years, it's also a correct system. I like the 2 leap days in 1 year idea. You wouldn't want to do that because you want to try to keep as closely synchronized as you can. All right. Everybody understand? Anyone want to ask a question here about it? Nope. All right. Then let's minimize that, get it out of the way. We're going to talk about the calendar. Why a 7-day week is the question of this slide. Darn it. I don't know why that gets turned off or why that gets moved every time. Why a 7-day week? What did you learn probably since you were a little child about why we have a 7-day week?
7 days, Sabbath.
Yep. For in 6 days, God created the heavens and the earth, and on the 7th day he rested, wherefore he blessed Sabbath day. Right. Or you can go to Genesis, and he looked at what he had made, and it was indeed very good, and he rested from his creation. And so we have a very strong religious reason for believing that we have 7 days in a week because of creation. And I believe that, just in case anyone thinks anything I say after this is going to undermine it. I believe that's the reason we have a 7-day week, that the calendar has been kept continuously by humans since creation. And so they've always stuck with the same thing for the most part. There have been attempts to change it. There have been ideas of, let's make a 10-day week. There are other things that you could come up with. For instance, back in the early days, they thought that there were 7 planets orbiting the Earth. And those 7 planets would be the Sun, the Moon, Mercury, Venus, Mars, Jupiter, and Saturn. And there's something that makes sense about that as a story. Right now, keep in mind, I believe that it's because of creation. But if you think about it, what's the name for the first day of the week? Sunday, because it's named after very clearly the sun. The second day of the week? Monday, named after the moon. You go through and Friday's named after, was it Friday? Frida? It's a... Okay. That's not one of the planets as far as I know. But you have, like Saturday is clearly named after Saturn. And for Monday, Tuesday, Wednesday.
Tuesday is named
Um,
after Thursday is named after Thor. Tuesday
yeah.
is named after Tyr.
Okay.
The middle days are named
After gods.
after Norse gods.
Yeah. Which are the best gods, second to the real gods. The real God, the Godhead, 3 in 1. Okay. Okay, so there are some reasons you might believe that that's the reason we have 7 days. There is no definitive historical work other than the Bible to give us a 7-day week. And it's generally accepted across cultures. Now, the month, the synodic period, the interval from new moon to new moon, is 29.53059 days. And we have about 12 of those in a year. And so we have months that are named, the name month after the moon. But we have 28 to 31 days in those months. And the development of those months is kind of interesting. Our calendar is not, strictly speaking, a lunar calendar. It's based with months being similar to the lunar period, but it's not the same. Some calendars are absolutely lunar. So, we have like the Chinese New Year. You ever get confused on when the Chinese New Year comes? Yeah, it's really confusing to me. But the Chinese New Year comes at the end of a solar or a moon cycle because their calendar, the months are based on the moon. And you just, every 3 years, you throw in an extra month to keep the calendar about right. And so the Chinese calendar shifts pretty dramatically compared to ours because they're essentially throwing in leap months. And the Jewish calendar is similar. Now, if this slide were to load, we had this problem before. Well, we had this problem before, and the slide actually reappeared when I came back to it after lecture. Was it in your class when the slides were blank? There were 2 that were blank. Must have been my other class. Anyway, they reappeared, so I don't know what was going on. It's got to be my software just didn't load it right. Okay, looking at the Roman calendar, we use essentially a Roman calendar that's been modified. If you go back in time, it's been used for a long period of time, but it's been modified. And notice the original may have had only 10 months and began the first day of spring. Why would we suggest it might have only 10 months? You've probably not thought of this, but when I say it, it's going to be real obvious. What are the last 4 months of the year?
December.
That's the last one, but the last 4. September, October, November, and December. What does the prefix sept mean? 7. The prefix oct?
8.
Nov? Dec? Right? Those months are just named the 7th month, the 8th month, the 9th month, and the 10th month. Of course, September is actually our 9th month and so on. So the names don't match where they come in our calendar. Question, Russell.
I think it's August and January that are the 2 new ones out of the list.
Well, August is Caesar Augustus. January, I think, is Janus.
Yeah, January. I knew January was a new one.
And July is Julius. Yeah. March is Mars.
May is.
I don't know May.
I think it's in Manila, maybe.
Anyway, it's interesting that our calendar has, these ancient historical things. And, we've all heard like, my month is August. Caesar Augusta, I am so great. It must have more days than the other months. So I'm going to take a day from poor February. And the variations on why we have February losing days, at least from what I have been led to believe, is
It was because Augustus wanted August at 31 days like July.
Yeah. It was grabbing days from other month to make his month more special. So let's look at, now we've already looked at the leap year system. The Julian calendar had the leap year system, but it was just every 4 years. The Gregorian calendar is modified to have not just every 4 years, but the additional skip 100, add back the 400. If you thought about those rules, okay, so by the first rule, add every 4th year, 2000 should have had a leap day. But by the second rule, 2000 is divisible by 100, and so it should have not had its leap day. But by the third rule, 2000 is divisible by 400, so it got back its leap day. So 2000 was a normal year. Most people would just have thought, yes, because that's the way leap year works. You have it every 4 years. I, knowing better, feel like I got ripped off because I had a chance to have a year with no leap day that was multiple of 4, but it didn't come around because of rule number 3.
1900 didn't have it.
Right, 1900 would not have had a leap day. But I wasn't alive then, Russell. I don't know how old you think I am. My grandfather was born in 1900. And I'm not going to be around in 2100, I'm pretty sure. So I missed my chance. You guys live long enough and you can, I knew that back when I was in high college, I learned. You have to be more than 100 years old then, though. Okay. Back when I was in graduate school, I had a roommate whose girlfriend was taking Bible studies from one of the guys at our church. I thought, that's great. They invited me to come along. Sure. So I come along, and the guy giving the Bible study is answering their questions. And my buddy says, okay, so we have the designation BC, which means before Christ, and AD, which means Anno Domini, or in the year of our Lord. So before Christ, did they use that system? And the guy giving the Bible study said, yeah, they've always used it. And he's like, well, how did they know what year, Christ was going to be born? Well, I don't know, but they did. Well, he was wrong. I had to look it up. We're Facebook friends, and so I sent him a post a few years back just clarifying that it wasn't until 532 with our current numbering system that this system was adopted. Right? So this system was not around the time of Christ. It wasn't like, wow, look who was born in year 1 AD. What a coincidence. It's not the way it worked out. But the system was devised based on calculations back of, okay, we understand this historical event. And as I understand it, it's off by a few years. Like, I think Christ was supposed to be born in something like 4 AD or something, 4 years after his birth he was born would be a way of reading that. I'm probably wrong on the actual number there, but he wasn't born on 1 AD. And the system does not have a 0 year. So you have 1 BC and the next year is 1 AD. But that's the way that we have been keeping time since 532 AD. So about for the last 1,500 years, give 15 or so. Currently, there is a push to try to take God out of the calendar. And so it has become common to replace BC with BCE. Why do they do that? Because instead of saying Christ, it says common era. And so you don't have to reference Christ when you talk about a year. And AD, instead of being Anno Domini, the year of our Lord, they just call it the common era. So there's a bigger shift there. And so if you see CE and BCE, BCE just means BC. CE means AD, and people use it because they don't want to reference Christ. I, of course, kind of like to reference Christ, so I kind of like to keep with the old tradition. Our first clicker question, do you all bring your clickers tonight? This is, by the way, changing topics. We're now caught up This is the topic I was supposed to start on.
What's the number for this class?
33 for your clicker. A or an. I don't know why I put an. It's not an hypothesis, it's a hypothesis. I don't understand people who put an before words that start with an H if it's a voiced H.
Did you just give us the answer?
What was the
Huh? No, if you look at the answers, I put A parentheses N so that it would fit all three of them, or all four of them. But then I said, well, I don't think I really needed to put the N because it really should be a hypothesis, a paradigm, a theory, a model.
What's the session?
The session ID is Web Astro. That's capital W, lowercase e, lowercase b, capital A, capital S, capital T. Oh, no O, ASTR. I said Astro. Okay, so obviously Jessica's getting that straightened out. Hannah, I don't have an answer from you yet.
I have to log back in.
And Aldwin, I don't have an answer from you yet. Now I
Wait,
do.
I'm almost there.
It logged you out?
Yeah.
Okay, Hannah's in and it's just Jessica. I do want you to actually get in because I think we only have 3 questions. And so, getting me, you could miss one, but if I don't get through all of them or something, then it hurts. Okay, everyone's answered. And every one of you said theory. And you're correct. Now, I want to review the scientific method here. The scientific method doesn't have the word theory in it the way we used it, right? Now, the scientific method has lots of different ways, and we have our simplified form. What was the first step? Like when it comes test time, what's the first step you're going to write down for scientific method? Observe something interesting. A lot of people would drop that one as a step, but I make sure it's in there simply to emphasize that science starts with a curious mind. You have, some point, maybe you'll become a father or a mother and you'll have a little kid, and that little kid's going to say, why is this? And why is that? And why the other thing? That's the mind of the scientist right there. And almost all kids have that curiosity. And the scientists are the ones that don't let their parents say, because, I don't know. But instead, try to help them figure out answers and encourages it. So the first step, find something interesting, observe something interesting. The second step, you create a hypothesis that has 3 things it has to do. Number 1, based on scientific ideas. That's where astrology fails. Astrology isn't based on scientific ideas. It takes scientific observations, but then just makes predictions that aren't based on scientific ideas. Number 2, it needs to explain why the observation occurred. And number 3 is it needs to make testable predictions. Astrology makes lots of predictions that are testable. You're going to have a good day. Okay, it's kind of hard to define what a good day is, but you're going to win the lottery. It's a good day to buy a lottery ticket. That's easy to test, but it's not based on scientific ideas. And then we have to do the test. And if it passes the test, we're not done. What do we do if it passes our test?
Test another, what's the word?
Prediction.
Prediction.
Yeah. Test another prediction of the hypothesis. If it fails the test, well, then your hypothesis is wrong. And you go back and you modify the hypothesis because you have new and improved information. And so the process is never done. But as you've done it more and more, so you have more and more observational and or experimental confirmation, you get more and more confident in the hypothesis. And if it can be applied a variety of ways, you say, yes, that's a theory. And if you can put a nice equation to it, you say, wow, that's a law. So theory is, as far as we're concerned in this class, it's a well-tested hypothesis that's to the point that most reasonable people think it's highly unlikely that it's wrong. It's still possible that it's wrong, but most reasonable people think it's highly unlikely to be wrong. Not every reasonable person, or else we would never, ever overthrow our theories, right? Okay, so now let's look at these other things just to make sure we understand them. What is a hypothesis?
Hypothesis?
Yeah.
Is an idea.
Okay, an idea, an educated guess is the best definition I have for it. Hypothesis isn't just a random answer. It's one that is educated based on knowledge, but it's still going to come down as a guess.
Say it's like a testable explanation.
It must have testable predictions.
Okay.
What about a model? Can you name a model that we've used as recently as yesterday?
The celestial sphere.
Yeah, I was going to say, if some Norway guy said that sitting up there on top of that bookshelf, the celestial sphere is a model. That up there is the celestial sphere. If you look at it after class, you'll see all the constellations and all the stars, well, not all the stars, mapped out on it. And we treat it as if the stars are on that sphere and we're at the center of it. But the stars aren't on a sphere. Some are relatively near, like, Alpha Centauri being just 4.3-ish light years away. Some are very, very far away, millions, billions of light years away. So they're not on a sphere. They're all over the place. But as we look at them, it appears to us like they're on a sphere around us, and it's a model that's useful to help us identify locations of stars. Paradigm, that word I have not used in the class, but you probably know it. So let's just make sure it is defined. I don't think it's going to come up on a test or anything, but it's useful to know, especially when you always have those, ooh, it's a paradigm shift. So what is a paradigm? I'll give you an example of a paradigm shift. In physics, of course, because what else would I give you an example in?
Who needs physics?
All of us do. I know he's joking, or I would be offended. Around 1900, physicists thought they understood the world. There were famous physicists who went on record in interviews saying, yeah, we understand pretty much everything at this point. There might be a few decimal places to add on constants, but we understand how the world works. And then in 1905, Albert Einstein wrote 3 papers, each one of which I believe, I am not on the committee, but I believe each one of those by itself was worthy of a Nobel Prize. He wrote one about Brownian motion that is explaining why when Robert Brown looked at a little grain of pollen floating in water, when he looked out with his microscope, he saw the grain moving. And Brown said it must be the result of, quote, cavorting beasties. In other words, microscopic living things were pushing on the pollen grain, making it move, was his conclusion. And Einstein wrote his paper and said, no, the still water actually has molecules that are moving very rapidly in it. And those molecules are hitting the grain, and it's so light that it's rebounding from the collisions with water molecules, which we now believe to be true. But it was a very big change in understanding. The second paper, I don't know about the chronological order, they were all 3 in 1905, was about a special theory of relativity. The whole understanding of relativity came from that. Nobody had any concept of what we now consider relativity. And the third one, the one that he actually got a Nobel Prize for, was on the particle nature of light. Everybody at that point thought light was a wave, and he provided an experiment that showed in this situation light cannot behave as a wave. And that led to the development of quantum physics, which makes things like my cell phone possible. So the whole framework of how we look at physics changed. The whole world of physics changed considerably because of those papers. And so there's a paradigm shift, a shift in the framework of how we look at something. And so that's what paradigm is. It's the framework in which we're considering something. Paradigm shift is you're considering it from a different perspective, a different framework. So that's not part of the class, but it's a question nonetheless that's good to know. What is the importance of the equinoctial colure? Something you have to know for the lab final. I am going to ask you during the lab final, what is the importance of the equinox? Well, you're going to have to point out, and then I'm going to say, and what is its importance? So you have to answer this one on the lab final. It is open for you to answer. Okay, thank you, Latifah. First answer. It is Latifah, right?
Yeah.
Okay. I was afraid that you were laughing because I mispronounced your name, and I don't want that to happen. Umas. All right, this time we didn't all agree. All right, so 7 people said it's equivalent of the equator on the celestial sphere. 1 person says the equivalent of the Tropic of Cancer. 3 says the equivalent of the prime meridian. Talk amongst yourselves. Get some competing opinions. If all the people at your table, Max, you got to talk to people at another table. If all the people at your table agreed, find someone else who disagreed so that you can get people's explanations of how they came up with their answer. I don't know. Remember, after we discuss an answer again, I am going to pull a card and ask somebody to answer.
That's what I was asking. That's what I should have, but I looked at it after I chose my answer.
You looked at it after you chose your
I
answer?
was like, looked at him like, he looks right, but I'm not sure. So I didn't just the worst
What is it? What?
Pulsar.
A pulsar? A pulsar is a name for a neutron star that is rotating so that its magnetic pole points at you. And you see pulses because of the, I can't remember the name of the radiation, but you see pulses caused by the radiation caused by the strong magnetic field going through space. How do you make one? Well, first you have to have a massive star that is, like around 3 solar masses die. I think it's too massive. Yeah, it'll go straight to black hole. I don't even know its mass. Yes, question.
You heard the whole thing about them finding the closest habitable planet to Earth. Will they think they found it?
Last I heard, it was one in Gliese 539 something, but I haven't paid enough.
I saw it the other day on IGN, and they said that there was one in potentially in Proximus Centauri. Well, it's orbiting Proximus Centauri.
That's actually hard to imagine because Proxima Centauri isn't giving off much radiation. Okay, go ahead and answer again now that you've discussed your answer with everybody. And I am drawing a card for who is going to answer out loud.
Good with me.
It is.
That's kind of like I had.
But I didn't know this one.
The next one.
You got to put your answer in first, sir. We're repolling.
Oh, are we doing it?
Yeah. Okay. This time around, our answers were 10, 0, 1. I was supposed to have been in blue, but it's okay. Okay, Alwyn, defend your answer.
I went with A, because, I made an educated guess. I'm gonna be honest. And then total educated guess and be like my friend Amelia said that they have the same root word. And so I'm kind of with that.
Okay.
I won't lie, I did guess.
And it's good not to lie. And it's good to explain your process there. Now, here's the sad thing. 3 people were correct, and their friends convinced them that they were not correct.
Oh, I was right the first time. Oh.
Yes, there is the equa in both of them. But remember, the celestial sphere has the celestial equator that is equivalent to the equator but on the celestial sphere. And it's got the full main equator, not just the equal part. The equinoctial, actually, I believe it comes because the equinoctial clue goes through the equinox. Equinox. Okay, so it's the prime meridian. It's a meridian. Remember, that's the line that goes from north celestial pole to south celestial pole that goes through the vernal equinox. For sure it's vernal. And that's where we measure zero right ascension from. We measure our longitudes from the prime meridian. We measure our right ascensions from the equinoctial clue. So that's the importance of it. And like I said, that's part of the lab final. It's something you need to know. All right. Those 2 questions were to start us off in a new direction, talking about the history of astronomy. So what you're going to learn today and probably tomorrow, I imagine some of the things are going to really surprise you because they're counter to what you tend to think the history of astronomy is. So we start with something simple. I told you I'm in this creationist group on Facebook, and there's these flat earthers who are constantly talking about there's no curvature. And if there's no curvature, then we can't be a ball. And, Aristotle, from observing the shape of the shadow the Earth casts on the moon, concluded that the Earth must be a sphere. The idea that the Earth was a sphere was proposed hundreds of years before the birth of Christ. And, I should add, was generally accepted hundreds of years before the birth of Christ. So when Christ walked this earth, educated people would have probably all agreed that the earth was a ball. And yet today, we have people who can't accept that idea.
Yeah, it's funny how they believe all the photos from space are fake.
Yeah, they're all faked. I mean, they do. Yeah.
That's a whole nother thing.
Yeah, they're just computer graphics. So it wasn't just the shadow. It wasn't just one line of reasoning. He also noted that if you go farther north, you can see some stars. You go farther south, you can see some other stars. You can see different stars depending on your location, north to south, which once again indicates you must be at a different angle looking at different parts of the sky, not just on something flat. Because if you're on something flat, you'd see the same stars everywhere. Their positions might seem to shift a little, but that's all. They'd still be visible. So we have Aristotle was over 300 years before the time of Christ, that the earth was a sphere. So if 350 BC, it was known, or it was determined, I say known implies a knowledge of science. We try not to use words like proven or anything. Then what was going on in 1492 when Columbus sailed the ocean blue? So the question here is, in 1492, who thought the earth was flat?
Who's Washington?
Excuse me?
Who's Washington?
Washington Irving is an author.
Was he from that time?
No, he was not. Now the 20 questions is over.
There's only like 2.
3, but I think it was 3. I don't know. Who was he?
And then
Yeah.
I wonder how Marco Polo became a game.
Became a what? Oh, a gang. I think he said a gang, and I was like, I've never heard of the Marco Polo gang.
People who lose to Italy.
It's kind of like,
People who lose to Italy.
I know who he is. I'm just wondering. Like,
okay,
how it
go
became-
ahead and get your answer in, and we can answer your question once you get your answer in. Okay. So if we look at our answers here, we have 2, 1, 0, 1, 5, 2, 0. Now, I'm going to first answer Alwyn's non-relevant question. How did Marco Polo become a game? What is Marco Polo famous for?
Traveling to China.
Okay, for exploring the world, traveling to China being his great
They only knew
exploration.
China was there. They just only knew China.
They
They only knew China was there.
Yeah, and he went there
I know.
and established trade routes. Okay,
The 3 boats were only there. They only had 3 boats.
I didn't know there were trade routes.
The one that have trade boats of the Chinese people.
But he's famous for being an explorer. And so Marco Polo, the game, what you're doing is you are trying to find something. And so it's based on that. It's exploring. Okay, so now that we've answered that, now Marco Polo was not part of this equation, and no one answered Marco Polo. Christopher Columbus, did he believe the Earth was a sphere? Yes, he did.
He just thought it was smaller than it is.
He just thought it was smaller than it is. He thought that the Earth was much smaller, which means he didn't pay attention to some of the information we're going to show in the next couple of slides. And so he calculated that it should be closer to go the other direction to get to India. And Queen Isabella bought into his "it's smaller than everybody thinks" idea. And so they certainly must have known the Earth was spherical. It wasn't some new idea. Sea captains, they sailed the ocean. They knew that it was a globe. Pretty much everyone knew that it was a globe. No one believed that the Earth was flat. I mean, they're no educated person. And so where does this idea that Columbus had this grand idea that the Earth was a sphere and everyone thought it was flat come from? It comes from a book written by Washington Irving, I think in the early 1800s. So that's a modern day fiction that is often taught to people as truth in grade school. So, Russell knew absolutely. The problem was Christopher Columbus thought that the radius of the Earth was smaller.
Don't you mean circumference? Don't you mean circumference?
Well, the circumference and radius are related by 2 pi, so one infers the other.
But he was thinking of it.
It's the same thing. Okay, moving on. So how do we have information and how long have we had it? Aristarchus, this is a little bit after Aristotle, but still in the same rough time frame from 310 to 230 years before Christ. He used the relative size of the shadow of the moon, or the shadow of the Earth, and the size of the moon to say the shadow of the Earth is about 3 times bigger than the diameter of the moon. And if we can assume the sun is far enough away that the sun's rays are parallel, that must mean that the Earth is about 3 times bigger in radius or diameter than the moon, which is pretty close. The actual fraction is 0.27. If he would have said a quarter, he would have been closer to right. Yes, that's true. But he was in the ballpark. But he didn't stop there. He also tried to estimate the size of the distance between the Earth and the moon by observing how long it took for the moon to go through the Earth's shadow. And he came up with the distance to the moon was about 70 times the Earth's radius. And it's about 60 times the Earth's radius. So that's in the ballpark. I mean, yeah, sure, that's more than 10% error, but it's less than 20%. It's not bad. But he didn't stop there. He then tried to estimate how far away the sun was. Unfortunately, he was dramatically wrong with his estimate for the sun. He said the sun was only about 20 times farther than the moon is. And based on that, he got the sun to only be about 7 times bigger than the earth. Those numbers were dramatically wrong. But he did some good work, especially considering when this was. Finally, now keep in mind this time. He lived from 310 to 230-ish years before Christ. He concluded that the earth was not the center of the universe, that the earth was going around the sun. Who have you learned came up with the idea that the earth went around the sun?
Galileo.
No,
Okay, Galileo, Copernicus, both of them believed and were proponents of the earth going around the sun. Most people give the credit to Copernicus slightly before Galileo. But all they were doing was reintroducing an idea that was established well before the time of Christ. Now, was it accepted before the time of Christ? No, it wasn't. Unlike the whole spherical nature of the earth going around the sun was not accepted. For good reason. One of the things the flat earthers always point out, the earth, according to the theory that the earth is going around the sun, we're going around the sun really, really fast. Many hundreds of miles an hour, thousands of miles an hour, I think. And so if you were driving your car at 1,000 miles an hour and you popped your head out of the window, you'd kind of feel it, right? And yet when you go outside, you don't feel it. Yes?
This is the same reason why you're driving 1,000 miles an hour in your car and you do it wrong. It doesn't really feel the outside effect. Okay, so it's relative to you.
Yeah, okay. I think you're right, but I'm going to go with my explanation. The reason is the Earth's atmosphere is rotating with the Earth and it's traveling with the Earth. So our atmosphere is stationary with respect to the surface of the Earth. Hence, we don't feel that breeze because it's just moving with us.
Yeah.
But that's an argument for the Earth not moving as we don't feel any breeze from it. Yes, it would. A second one is that we don't see any parallax. Now, the parallax idea is a little more complicated. So let me use the simple example. Okay, if I stand right here, I look at Latifah, and she is to the right of Gabby. And now if I walk over here, now Latifah and Gabby are lined up. And I keep going, and now Gabby's on the right of Latifah. They didn't move, I moved, right? So this parallax idea is the relative position of things in the distance appear to shift as you move. Well, astronomers back before the time of Christ didn't observe any kind of parallax. They didn't observe one star moving relative to another throughout the seasons. And so they said, well, if the Earth was moving, we should observe that. But these guys weren't idiots. They were able to do some pretty detailed work. And they said, we don't observe that, so the Earth must be stationary. Finally, if you're riding a horse or riding in a horse-drawn carriage, either way, you're going to feel lots of bumps and bounces as you move along. And we don't feel bumps and bounces. And so once again, that was something that led to the conclusion that the Earth must not be moving. So it wasn't sheer ignorance that made them reject this idea that the Earth was going around the sun. They had what they thought were some good measurements. Now, with the advances we've had, we now have telescopes. They didn't have telescopes. And with telescopes, we can measure parallax. And so now we can make direct measurements to say, yes, we must be moving because we have that parallax. And there are hundreds of stars that parallax can be measured from Earth, and using satellites, there are thousands more. So we can make lots of those parallax measurements. So now we have evidence that gives us very strong that the Earth is going around the sun. But back then, more than 200 years before Christ was born, there was the idea being floated around that the Earth went around the sun. Now we get to Eratosthenes. Note we're moving forward in time, progressing in time. We're now up to, he died 195 years before Christ was born, 195 BC. Assuming no little errors there. And he wanted to know the size of the Earth. And he noticed that in this town of Syene, on a certain day at noon, the sun shone all the way to the bottom of a well. And he said, well, if the sunlight goes all the way to the bottom of the well, the light goes in a straight line, the sun must be directly overhead. And so then he had somebody measure the angle the light made with vertical in Alexandria at the same time that it was straight above the well. And the measurement was 7 degrees. And taking the distance between Syene and Alexandria and that 7-degree angle, he was able to calculate then, 7 degrees, there's 360 degrees in a circle. So you take that distance, multiply it by 360 and divide by 7, and you get the circumference of the Earth. And so he was able to calculate, circumference is just the pi times the diameter. So he's able to calculate the diameter of the Earth almost exactly correct. Which is, I think that's amazing, given what he had to work with, that he was not only that the Earth is a sphere, but what its diameter is, known 200 years before the time of Christ. Obviously, Columbus didn't buy into Eratosthenes' work. Sticking with this, just one more thing before I go to this new topic. We're talking about small angle formula here and angles in general. What I've laid out is history you don't really hear about. You tend to think that it's modern discovery that the Earth goes around the sun and that the Earth is a sphere. But this is, anything to me that's before the time of Christ is really quite ancient, that it was discovered. And so our progression isn't as rapid as we tend to think. We have, as a society, tended to all reach agreement on these ideas, but they're not all that new. Now to angles. Remember we had the slide that gives your hand as an example for measuring angles. Because when we're looking at things in the sky, they're very far away. And you can't really say, that's 1 meter from there to there. But what you can do is measure how big the angle is something takes up. And so we have the hand, and it was 20 degrees going from thumb to pinky. As a general rule, if you hold your hand an arm's length away. Right now, that's not going to be exactly the same for everybody, but pretty much the length of your arm, the size of your hand, should scale roughly, so it's reasonable. And the thickness of the thumb was 2 degrees, thickness of the pinky about 1 degree when held at arm's length. So those are just easy ways to kind of keep track of sizes and separations of things in the sky. So when we look at things in the sky, we'll say, the moon is, I think it's about half a degree of angle it takes up in the sky. And so we say, it subtends an angle of half a degree. Oh, yes, there it says. For example, the moon subtends half a degree. Look at that. Imagine it. It turns out the sun also has just about the same angle. I saw an annular eclipse. An annular eclipse is an eclipse that looks like an annulus. An annulus is a fancy word for a ring. The Earth is sometimes closer to the sun and sometimes farther. We talked about the seasons are not caused by that. The Earth is closest to the sun about January 4. And that doesn't make it summer. It is summer in the southern hemisphere, but not here. But on January 4, we're closer to the sun. That means the sun is going to look a little bit bigger in the sky. It's going to make a slightly bigger angle. And so if we were to have the moon pass between us and the sun close to January 4, the sun would make a bigger angle than the moon does. And so when the eclipse happens, we'd see a ring of sun around the blocked disk of the moon. Now, it's not just the sun that gets closer and farther. The moon also gets closer and farther from the Earth. So, I got married May 27, 2012. It was in May when we saw the annular eclipse. The sun was about, the Earth was about halfway between its closest and farthest from the sun. But the moon was obviously farther than normal from the Earth, so that it was making a smaller angle than the sun to give us the annular eclipse. Now, in 1 year, on August 21, we will have a total eclipse here, which means at that point, we will have the angular size of the moon bigger than the angular size of the sun, so it completely blocks it. Okay, our first real math, the small angle equation. The equation that essentially Eratosthenes used to calculate the circumference of the Earth. If we make a measurement of the diameter of an object, so L is the diameter of the object, and we relate that diameter to the angle it makes up, the angle is, okay, theta, I shouldn't use theta because, we're just not going to. The angle is equal to the diameter divided by diameter of object divided by, instead of radius, I'm going to put distance to object. This is actually a mathematical definition of what angle is. But that equation is in the natural units of angle. When you measure angle, what units do you typically use? Degrees. But degrees are simply based on how much the Earth orbits around the sun per day. There is a natural angle that's called the radian, and the radian really has no unit at all. And this equation here is what defines an angle in units of radians, which is no unit at all. Notice diameter is the length, distance is the length. Length divided by length means you have the units cancel out. So that's actually the definition of an angle. Well, if we want to relate the angle to the size of something, we can use this relationship, but we tend to use a conversion factor to get it into units of degrees. But before I go to units of degrees, there's one more thing I need to go through. We have on the clock hours, minutes, and seconds, right? There are 60 minutes in an hour, 60 seconds in a minute. When you measure angles in degrees, we measure the angles in degrees, minutes, and seconds. And just like with the clock, there's 60 minutes in a degree and 60 seconds in a minute. And so for angles of things in the sky, we tend to use arc seconds as our units. And so we have this equation here, but if we want an angle in arc seconds, then the angle in arc seconds is equal to the diameter of the object divided by the distance to the object. And then we have to have the conversion factor for using arc seconds, which is one over 206,265. And so that 1 over 206,265, that's just a conversion factor to go from the unitless radians to arc seconds. And actually, no, it should be multiplied by 206,265, not divided. Got that backward. That's what happens when you don't review carefully. We multiply by 206,265 to get it into arc seconds instead of being in the much bigger radians. So we're going to use this equation. We will have something like you measure an object and it makes up this angle in the sky. And if we can determine it's this far away, what is its actual diameter? And so you're going to have to take this equation and solve it for the actual diameter. And so this equation will be used multiple times. It'll actually come up from now until the end of the class periodically in homework. So it's an equation we're going to have to use from time to time. Here. There's the equation with 206, 265 in it. The L is the diameter of the object, and the D is the distance to the object in that equation. And so it shows you how that conversion factor comes about, the 360 degrees per 2 pi radians, and then the 60 minutes per degree and 60 seconds per minute. So this equation on the test, it'll be given to you. And you have it in your textbook, you have it here. So you don't have to memorize the equation, but you are going to have to be able to use it. Question?
Making me not memorize it.
Yeah, you bet.
I would fail that immediately.
In physics, we're really not concerned about students being able to memorize stuff. We figure anybody can memorize. You just have to sit down and spend the time, right? We're more concerned about people understanding how things work. I'm going to skip right over that. Models for the solar system. The model that Aristotle came up with was a model that said that each of the planets is on a crystal sphere. Crystal because crystal was his perfect material. Sphere because sphere was his perfect shape. And they're rolling around. And in fact, one of my colleagues at PUC found sheet music for the music of the spheres. It was really, really boring. It was like, well, one of them was like Jaws. Or, yeah. But it basically had as many notes in it as how far it was from the Earth. It was kind of boring. So I was like, da, 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 da. Okay. None of them went, okay, I'm not going to. So that's the idea that Aristotle had. That idea was demonstrably wrong. It was demonstrably wrong because, and this is one of your homework questions, because we have retrograde motion. That is, if you look at the motion of a planet from one night to the next, you see that sometimes they tend to look like they're going backward. So here's a picture showing if you were looking from Earth to Jupiter, let's say. And if you go in successive nights and you look where Jupiter is in the sky, you see that Jupiter tends to be moving to the east each night. Compared to the stars, Jupiter's moving east. That's the normal motion, what we would call prograde motion. But as the Earth catches up to the planet, and I'm not going to have you do this tonight because I'm lecturing, for more than an hour. Otherwise, we do the I swear. Okay, here we go. As the Earth catches up to the planet, you suddenly have, it appears to go toward the west. So you have Jupiter was marching every night, marching to the east compared to the stars. All of a sudden it stops and starts marching west. And then starts marching east again. And Aristotle's idea of all the planets just going around in circles on those spheres simply can't explain this retrograde motion. But of course, Aristotle, who wants to argue with Aristotle? He was considered the greatest mind. So Ptolemy came up with this idea that was a variation of Aristotle's plan. He said, okay, yeah, there is a crystal sphere out there that the planet's going on, but it's not just on the sphere. It's got a little circle that it does as it goes along the sphere. So when you were kids, how many of you played with the spirograph? Really? Only one? Well, with the spirograph, you essentially did this. You had a big circle, and then you had a smaller circle with little holes in it, and you take your pen, you move it along, and it makes little pretty squiggles that loop. That's the idea that Ptolemy had. That the planets are on those little ones that are rolling on the big ones. And the planets are on the outside of that wheel, and so when they are on the inside portion, so when they're on the inside portion here, they actually appear to go backward because of that relative motion of the wheel compared to the big sphere. And so Ptolemy called these little circles epicycles. And the big circle was the deferent. And so with this, he could take Aristotle's model and alter it so it actually explained the retrograde motion. Now, he did some other things to Aristotle's model. He also said that instead of the Earth being the center of the universe, that the center, if the center is here, then the Earth is actually here, and there's this empty space here that everything's going around. So he had another little modification there. One more thing he had to have. Mars and Venus never get that far away from the sun when you look at them, the angular space. You never have the sun over here and Mars and Venus over there. Venus and Mercury, wow. Mars does go over there. Venus and Mercury. Mercury gets around 45 degrees of elongation, about 45 degrees away from the sun. And Mercury is somewhere in the ballpark of, I think it's 27-ish degrees away from the sun. They never get that far away from the sun. And so we can't have them going around the way that Aristotle had it. So he further added that you actually have, I'm just going to draw. I can't draw it here. Here we go. On this picture, I can kind of, let me make a new picture. We've all looked at these. Page manipulation. Insert a blank page just so I can draw one thing. So Ptolemy's model has the Earth here. Here's the sun going around a circle. And Mercury, I got Mercury and Venus in the wrong positions when I talked about the angles. Venus is the one that makes like 45, and Mercury is the one that's the smaller angle. Mercury and Venus are pinned on the line connecting the sun and the Earth. And that helps explain then why they can't get more than certain angles away from the sun. And then if you go beyond those, then you have the big circle, which is the deferent, and then the small circle that's the epicycle. And so they're rolling along. It's got to go this way. Rolling along that deferent in their epicycles. It's pretty complex, but it explained the positions of the planets every night. And that model was the dominant model for 2,000 years. That's a long time for a model to last. It's really, really hard to argue against that model. So when we get to Copernicus and him bringing back the idea that the sun is the center and not the Earth, it was a really hard challenge for him. As we'll see, Copernicus, he didn't garner acceptance because the predictions of his model with the planets doing circles around the sun were no better than the predictions of Ptolemy's convoluted model. Now, you guys have probably heard of like Occam's paradox, Occam's razor, and probably not in the context of Stargate SG-1 either. But Occam's razor says if you have two equally correct explanations, that each one gives the right answer, that the best one to choose is the simpler model. Well, when we get to Copernicus, his was simpler. But people didn't accept it because it had 2,000 years built into this old paradigm. And so it's hard to take the simple one even when it is simpler, and Occam's razor says you should select it because your heart is in something else. You have been indoctrinated. Okay, this is actually our last section before we go home. Learning some vocabulary words. Vocabulary words, yeah, that's not very fun. I don't make you memorize equations, but I make you memorize vocabulary words. So here's some vocabulary words. We have the word conjunction, superior conjunction, inferior conjunction, opposition, quadrature. That's a lot of words. So let's make sure we understand what they mean. So first of all, opposition. Opposition is the easiest one. If something is in opposition, that means the sun is here and it's opposite to it. So if you look there, a planet that is farther away from the sun than the Earth can be in opposition to the Earth. If a planet is closer to the sun, it can never be on the opposite side of us from the sun. It has to be farther. You know what we call planets that are farther away from the sun than we are? We call them superior because they're above, not better, but above. Ones that are closer to the sun, we call them inferior. Not because they're worse, but because they're below, closer to the sun. So only superior planets can have an opposition. Question marks.
Oh, you answer it.
Okay, excellent. So opposition is our easiest word. The conjunction is a word that means it's lined up with the sun. And so we have three forms of conjunction. Inferior conjunction, superior conjunction, and just plain old conjunction. So let's start with plain old conjunction. Plain old conjunction is the only kind of conjunction you can get with a superior planet. Superior planets, ones that are farther from the sun from us, it's either in opposition, if it's on the opposite side as the sun, or in conjunction if it's on the same side as the sun. It's always going to be beyond the sun if it's on the same side as the sun. Inferior planets can be between the sun and us, or they can be on the other side of the sun. And so that's where we have inferior and superior conjunctions. The inferior conjunction is the planet is between us and the sun. Superior is it's us, sun, and the planet. But remember, inferior and superior conjunctions only apply to inferior planets. So we have to know what an inferior planet is for that to even make sense. The last two words are quadrature when a planet is at a 90-degree angle from the sun. That's what the quadrature is. So in the picture you can see that's a 90-degree angle. That's what defines the quadrature. Max.
A 90-degree angle with respect to the Earth, right? Because technically, unless the planet is, directly lined up with the sun, it's always at a 90-degree angle to the sun with respect to something. You can always draw a line.
Yes, it is the line going from the Earth to the sun and the line going from the Earth to the planet. Yeah. So those are some vocabulary words just for identifying positions of stars. Now, or stars, planets. Is Mars a superior or inferior planet to the Earth? It's superior. Right. That's okay, because I made the mistake earlier in this very lecture. I don't hold it against anyone when they make the same mistake I do. Mars is the next planet farther away from the sun than the Earth. So it's a superior planet. As a superior planet, which of those four, the opposition, inferior, superior, and regular conjunction, can Mars have?
Conjunction.
Hmm?
Conjunction.
Okay, you can have a regular conjunction and opposition. So Mars can have those two. When Mars is at opposition, what time of day are we going to see it in the sky? Middle of the night, because it's on the opposite side of the sun. And if you look at the picture, it's pretty clear Mars is much, much closer to the Earth when it's in opposition than it is when it's in conjunction. So the angular size of Mars is going to be much bigger. Now, much bigger doesn't mean it's big. It's still a little tiny thing. But it's going to be the biggest, so you got your telescope, it'll be bigger in the telescope, or even your binoculars, when we are in opposition to Mars. And so that's the best time for viewing Mars, when it's in opposition. When Mars is at conjunction, it's the farthest away. What does that tell us about its angular size?
It's tiny.
It's the smallest it can get. And what time of day is it going to be in the sky? It's on the same side as the sun, so what time of day is it going to be in the sky? The daytime. It's hard to observe a planet in the daytime. So observing Mars when it's in opposition is a waste of your time.
I'm gonna do it one day.
Conjunction, what did I say?
Opposition.
I am so glad you guys corrected me. Right? If I go home and I realize I made a mistake, I'm going to stay up awake all night. Like, it's so much better to be corrected. Now, if we're looking at, let's say, Mercury, the closest planet to the sun, there's never going to be a time when Mercury is very far from the sun. So that means observing Mercury is kind of tricky. You can observe it sometimes in the early evening, sometimes in the, just before sunrise, but you're pretty limited in its observing. Whereas superior planets, you have, high in the night sky is the best observing. Question, Matt?
Yeah, it's. I was just thinking about quadrature. Does it only apply to planets that are superior because you can't get a 90-degree angle?
That's right. Okay, so Copernicus started his work by using these positions and doing calculations. And so here is the definitions for each of the words: opposition, when the Earth lies directly between the sun and the planet; conjunction, when they're in a straight line; quadrature, when it's 90 degrees. And a clicker question about these words: what term is used when Venus passes between the Earth and the sun? And yes, it's one of those. I don't know why I was thinking I should give you options. They're already there. Too bad I'm not going to call on you again then.
Oh, you will.
Only after I've called on everyone else.
Somehow, my luck, I'll be nice.
Okay, Jessica, Connor, and Hannah. Jessica and Hannah.
I'm saying sound incontinent.
And it's going to be out here. It logged you out again?
It's just saying downloading content and it won't let me answer when it's there and all the options are there. It just won't submit my answer.
Huh.
Yeah, I don't know.
That's troubling.
Yeah.
Okay, I think we have enough that's not going to hurt you to move on. So we had 7 people said A, 2, change colors, 7, 2, 1, 0, 0. Okay, we have a pretty good majority, so I'm just going to go straight to Russell Robinson. Russell, defend your answer.
Why it says in inferior conjunction?
Okay, so the first thing is you tell us which one you chose. You chose inferior?
Yeah.
And why did you choose that?
Because Venus is in the inferior set of planets.
It's what?
Inferior set of planets.
Okay, it's an inferior planet,
So it can't have an opposition.
right?
And it's not on the other side of the sun.
Yeah. And in fact, the fact is, if it says an inferior, or excuse me, if any planet passes between us and the sun, that's the definition of an inferior conjunction. It's going to have to be an inferior planet to do it, but that's the definition of inferior conjunction. So, good job. We had 3 people who had other answers. A superior conjunction, it would be Earth, Sun, and then the planet. And inferior opposition, doesn't exist. Superior opposition, well, we don't use the word superior, it's just an opposition. And of course, quadrature is not in line. Okay, I'm actually going to stop here. I think it's a reasonable place to stop. I did have the numbers close, except for I had the planets opposite. Mercury is 28 degrees elongation and Venus 47. I said 27 and 45, but I had Venus and Mercury backwards. So we'll pick up here tomorrow.